Hello everyone. So in this session we will be covering the first law aspects when applied to an open system. So in a closed system, you know that only energy can cross the system boundary in the form of work and heat. But in the case of an open system, you can have mass flow, which is also another form of energy transfer, along with heat and work transfer across the system boundary. So let us begin. First law applied to open systems. So the principles applied in the analysis of open systems are conservation of energy as well as conservation of mass. So both these principles will be applied to open system or control volume. Another control volume is another name for open system because the volume will get changed. On the other hand, a closed system is also known as controlled mass. Okay. So mass and energy content of the open system may change, it is not necessary, but there are every chance that it may get changed when the mass enters or leaves the system, open system. The example of open system includes fans, turbines, compressors, nozzles, pumps. All these are heat exchangers. All these are open systems. So thermodynamic processes involving control volumes, that is open systems, can be considered in two groups, which can be steady flow or unsteady flow depending on the variation of the properties with respect to time. So during the steady flow process, so in any case there will be flow of mass. Flow means there will be some mass entering across the system boundary into the system or out of the system. The fluid flows through the control volume steadily. That is constant with respect to time. No change with time at a fixed position. At a particular position with respect to the system, the property will not change with respect to time, the fluid flow. So here we can see a lot of examples for open systems. So in this pressurized water reactor, there are different components, right? There is a pressure vessel which creates a pressurized water. Then we have a boiler which creates steam. Fine. So heat will be transferred from the nuclear reactor to the water in this pressure vessel. Then in the boiler or the steam generator, that heat will be utilized contained by water to produce steam. And again, so everywhere if you see whether in the pressure vessel or in the steam generator, there is mass inflow as well as outflow. Again, you can have a pump also which is used to pressurize the liquid. Again, that is an open system. Here you can see a turbine. That is another open system. Again, heat exchanger used in the condenser. Again, that is open system. So this is a combination of open systems, right? So conservation of mass, if you look into it, you can write as sum of rate of mass flowing into the control volume. Open system. Control volume is another name for open system. Minus sum of rate of mass flowing from the control volume. So some mass is flowing into the control volume and some is going out. The difference between these two will be stored inside the system. That is the rate of change of mass flow rate inside the control volume in kilogram per second. So m and a dot on top of it will represent rate per unit time. M is having the units of kilogram, m dot is having the units of kilogram per second. So coming to the process which is well described by steady state steady flow process. So steady flow, you know that now. When the flow is constant with respect to time or there is no change at a particular position in a control volume with respect to time, then that is known as a steady flow process. Steady state process. Steady state, that's The states of mass streams crossing the control surface or boundary are constant with it. That is steady state process. So steady state, steady flow process could be well established to the devices, most of the devices, energy conversion devices, as we have seen in the previous slide in a power plant. So most of the energy conversion devices, if you look carefully, you can see that they operate steadily over a longer period of time. That means the rates of heat transfer as well as work crossing the control surface are constant with time. There won't be much variation. So we can assume these devices are operating under steady state, steady flow conditions. So under these conditions, the mass and energy content are constant with time, or mathematically we can write d by dt of mcv, that is the mass of the control volume, or delta m dot cv is equal to 0. There is no change of mass flow rate within the system. Now, before deriving the important equation from the first law applied to the open systems, that is steady flow energy equation, we will see in detail and understand what is flow work. This is very important. We have studied displacement work or boundary work in the closed system in a piston cylinder arrangement. Now here we are going to learn flow work, which is applicable for a flow device, that is an open system. So energy flows into and from the control volume with the mass, you know that, right? So this is a control volume. Some energy is going, this is an imaginary piston. Some imaginary pistons are provided, shown just for your understanding. So the energy required to push the mass into or out of the control volume is known as flow work or flow energy. Suppose some mass flow is there, this is the control volume, an open system, let it be a turbine or a compressor or a nozzle, something like that. Okay, which is having the volume of V, pressure of P and mass of M. Now, suppose you need to push the mass coming through this line, conduit, into the control volume, there is a necessity of certain energy, right? Isn't it? Through this distance. So mass is now at this point. If you want to make the mass move into this control volume, we need to apply certain force on this imaginary piston F. Okay. So the area of the piston is A and it should move through L. That mass should move through L, or the piston should come here so that the entire mass of the fluid will get into this control volume. Fine. So that energy requirement is termed as flow work or flow energy. Let us write in the mathematical form. So the fluid stream of the upstream, this is upstream of the control volume, control surface, just a minute. The fluid upstream of the control surface acts as a piston. So the fluid just behind the control surface, that acts as an imaginary piston that will push the unit of mass into or out of the control volume, as I have shown in the previous slide. You can see here. So this fluid just before this control surface will act as a piston and will push the mass into or out of the control volume. On the other side also it will happen the same way. Here also the mass here inside the control volume will push the mass away in the opening. So as the fluid upstream pushes the mass across the control surface, work done on that unit mass is the flow work or flow energy. That is the force multiplied by the distance or displacement through which the mass displaces. Okay, F into L, or you can write FL into A by A. Just to rewrite it mathematically, we are just using A by A. It is one, right? So now you know that F by A is P, force per unit area, normal force exerted per unit area is pressure, and the area multiplied with the length is nothing other than volume. So it is P into V, pressure multiplied with V, or V you can write as the mass into specific volume. Unit mass of the fluid flowing multiplied with its specific volume, mv, P into mv. Or this is the total work, total flow work, or specific flow energy or specific flow work, that is flow work per unit mass could be written as P into specific volume. Pressure into specific volume is the specific flow work. So the term PV is called the flow work done on the unit of mass as it crosses the control surface. So that term, mathematically, the flow work or flow energy is P multiplied with V. Now the total energy of the flowing fluid, is the energy carried by a unit of mass as it crosses the control surface, that is the sum of internal energy, flow work, as we have discussed now, potential energy and kinetic energy. So there will be internal energy, you know that, U, potential energy PE, and kinetic energy KE. In addition to that, since it is an open system, there will be flow work. So internal energy, kinetic energy, and potential energy were the same as in the case of a closed system. So in addition to that, we have now flow work, that is PV. So we can write the total energy carried by unit mass as it crosses the control surface as theta. Let us designate this as theta, which is the sum of internal energy plus flow energy plus kinetic energy plus potential energy per unit mass. Okay, unit mass of a substance. That's why we have used all the specific quantities: specific internal energy, specific volume, specific kinetic energy, and specific potential energy. So we can write U plus V. You know that it is enthalpy. Internal energy plus pressure volume energy is nothing other than enthalpy. So enthalpy plus kinetic energy plus potential energy is the total energy carried by a unit mass of a substance when it crosses the control surface. Now, if a certain mass m is flowing through the control surface, across the control surface, we can write the total energy carried by the mass of the fluid. Total energy carried by that mass of fluid when it crosses the control surface could be designated as E of the mass. Total energy of the mass is m multiplied with theta. Okay, m multiplied with theta, or m into h plus v square by 2 plus gz in kilojoules. This is the total energy. So here it was kilojoules per kilogram. Now when you multiply that with kilogram, m kilogram, it will become kilojoules. Okay. So make a clear understanding of these concepts before we start deriving the steady flow energy equation in the upcoming session. So we'll meet with the derivation of steady flow energy equation in the next session. Till then, goodbye. Thank you.